Шановні пані та панове, давайте ми під оплески Dear honored guests, so I have great honor invite to the stage Nobel Prize winner Кіп Торн. Your applause.
It is a great honor for me to be invited to give this lecture because I so admire the people of Lviv, the people of Ukraine, for standing up to Vladimir Putin and the Russian invasion. You are our first line of defense. If you fall, then the rest of Western Europe is in great, great danger, and we in the United States as well. And so we stand with you, and my being here, I hope, is a symbol of the way in which we do stand with you. Thank you. Let me just add that yesterday I met with the mayor of your great city, and he gave to me this bracelet that says unbroken, and I do see that that is the spirit of the people of Lviv, unbroken, and I admire you for that. Let me begin by telling you a bit about the making of the movie Interstellar. In October 2005, let me just back up, I missed a slide, September 1980, Carl Sagan, who was an astrophysicist but also a filmmaker, he made the movie Contact, for example. Carl Sagan introduced me to Linda Obst. Linda was a movie producer, just arrived and started producing movies in Hollywood. She wanted a blind date with me. I thought that was very strange. But she had actually been a science editor for the New York Times before she came to Hollywood. And so evidently that was connected with it. Linda and I had a brief romance, but it did not go anywhere. She was much too intense for me, and I was too much of a nerd for her. But we became good friends, and 25 years later, in October 2005, Linda telephoned me and said, "Would you like to brainstorm with me for a movie?" I thought about it for a few milliseconds and said yes, because it seemed to me this would be an opportunity not only to have fun, but also perhaps to be able to inspire people around the world about science. So that became my goal. We wrote a treatment for the movie Interstellar. A treatment is a description of the story of the characters, but most importantly, in our case, which is very unusual, the science that was built into the movie from the very beginning, and it was a lot of science. In February 2006, Steven Spielberg signed on to be the director of this movie. And so in my first meeting with Steven, I said to him, I would propose that nothing in this film will violate firmly established laws of physics, and all of our firmly established knowledge, or our firmly established knowledge of the universe. And all speculations about poorly understood physical laws in the universe will arise from real science. Stephen was enthusiastic to make a movie of this sort. He had never worked with a scientist before. And so Stephen and Linda brought on board Jonah Nolan, or Jonathan is his official name. And Jonah Nolan read many relevant science books, which I gave to him. He was going to be the screenwriter, so I gave him science books that were relevant to this movie. And he brainstormed with me. Brainstorming is basically talking back and forth to try to develop ideas. He brainstormed with me about the science in the movie. And by 2010, he had gone through, working with me and talking with Spielberg, 3 drafts of the screenplay, the script for the movie. Then on June 8th, 2010, Spielberg dropped out. He left the project. This may seem strange, but it wasn't strange at all. Spielberg has a style where he carries along in the early creative phase of a movie. He carries more movies than he can possibly make. And he decides when he's about to go into pre-production which movie to make and which to turn over to somebody else. And he decided he wanted to make the movie Lincoln about the American President Abraham Lincoln, who freed the slaves, rather than Interstellar. Interstellar was a science fiction movie. He had done science fiction movies before. So he opted for Lincoln. And we were left for 2.5 years with no director. However, Christopher Nolan, the brother of the screenwriter that we had, Jonathan Nolan, Christopher Nolan had told us already, even before Spielberg dropped out, if Spielberg leaves, then I might want to become the director. But he has a completely different style. Nolan never commits to a movie until his previous movie is completely finished, has been out for 6 months, and he's had time to think about what he's going to do next. So we waited 2.5 years for him to finish the movie Batman: The Dark Knight Rises. And then he said, I do want to do this movie. He has a very strong intuition about science, which comes amazingly from browsing the web. No formal training in science, but he's learned an enormous amount of science from the web. And he accepted my guidelines about not violating physical laws to the extent they do not get in the way of making a great movie. He was afraid I would be the policeman telling him what he could do and what he couldn't do. I was afraid he would take the movie in some crazy direction that was a total violation of the laws of physics. But as we started to talk together, within a few hours, it was obvious that we really wanted the same thing. We were very committed to getting the science right if we possibly could, and that we had good rapport and would be able to really work together. In fact, working with him became one of the greatest pleasures of my entire life. He's just fantastic to work with. He brainstormed with me about the science through 3 more drafts of the screenplay. The final screenplay and the movie preserved Linda's and my science vision. They added a large amount of new science that came from my brainstorming with both of the Nolan brothers. But they changed the story and the characters of the movie in major ways. So in the end, Interstellar is truly the Nolan's movie, Christopher and Jonathan Nolan's movie, and not Linda Opes and my movie. But the science is truly joint science. It's my science, modified in some very major ways and with a little bit of new science by the Nolan brothers. Very late in this process, I decided that I was going to write a book about the science in this movie because I saw this as an opportunity that, having inspired people, particularly the young people, about the science through this movie, this would be an opportunity for me then to educate them, to explain the science, and thereby get people who had been inspired hooked on the science. And in fact, this book, The Science of Interstellar, that I wrote, did succeed tremendously well. Practically every country I have visited, and that must be several dozen countries, maybe 30 or 40 countries since then, some young person, in many cases many young people, have come up to me and said, I have become a scientist, or I'm going to become a scientist because of this movie. And so I'm very proud of the impact that this has made. And in fact, this book also is used in many universities in science courses, in beginning science courses or courses on science for non-science majors. For example, it has been used for many years at Harvard University. Well, let me move into the science that is in the movie. And let me tell you this, that if you look in the upper right-hand corner, you're going to see an F or an S. Where it says F, that means that the science that I'm talking about is rather firm. We understand it. This really follows well-understood science. If you see an S, that means that the science is speculative. We have still followed the science, but there's a lot of speculation, that's speculation based on real science, but speculation. Okay. Let's begin with the relativity of time. If you've seen the movie recently, you will recall that Cooper, talking to his daughter Murph, says, when I'm in hypersleep or travel near the speed of light, or most relevantly, when I'm near a black hole, time will change for me. It will run more slowly. When I get back, we'll compare. We might even be the same age, you and me, and imagine that. And in fact, what Christopher Nolan said to me early in our discussions about this movie, that on Miller's planet, this is the water planet in the movie, that 1 hour on Miller's planet should be the same as 7 years back on Earth, or 7 years in the Endurance spacecraft that's up at high altitude in orbit around the black hole. 1 hour in 7 years is an extreme amount of slowing of time. When it corresponds to a factor of 60,000 in the slowing of time. When Chris asked for that, I said that's impossible, and Chris immediately said, go do a real calculation. That's because he had become accustomed to me by then having an immediate intuitive response to something he wanted, and sometimes being wrong, and having to go do a real calculation to be sure that whether I was right or wrong. So I went and did a real calculation, and I found that indeed, if the planet is just outside of the black hole's innermost stable circular orbit, that's what we call an ISCO. That's the nearest the black hole the planet can get without falling into the black hole. If it's just outside that, so it can go around and around in orbit and not fall in. And if Gargantua, the black hole, does not spin, then the slowing of time is only about a factor of 2/3. A small amount of slowing of time, not 1 part in 60,000. And so that would not work. And that's what my intuition was based on. However, I found that if Gargantua spins fast, and I was figuring this out using the laws of Einstein's laws of general relativity, in particular, if the angular momentum of spin of the planet, of the black hole, divided by the maximum possible angular momentum the black hole could have, is 0.9999999, all those nines, 1 part in 10 to the 14 in scientific notation. Then the ISCO is moved in much closer to the horizon, and in fact, 1 part in 60,000 slowing is possible, though not very plausible astrophysically. It would be very, very hard to achieve this in the real universe. But the rule that we had adopted is if it's possible, then it's fair game. We can use it in the movie, and so we chose to use it in the movie. So let me now talk about the orbit of Miller's planet. Here is a drawing of Miller's planet, and I want to take an equatorial slice through the planet. It's a 2-dimensional plane that cuts the planet in half. And I want to look at the geometry of that plane. And you would expect it's the same as the geometry of a flat sheet of paper, but it's not. In fact, the circumference around the black hole is very small compared to the diameter. And so, in fact, this is what it looks like, the geometry. And in order to visualize this, you have to imagine that our universe is embedded in a flat, higher dimensional universe. So I add one more dimension. We have 3 space dimensions in our universe: east, west, north, south, and up, down. So that's 3 dimensions. And we're adding in a 4th space dimension, or in the movie it's called the 5th dimension because time is also a dimension. And so the 4th dimension is taken up by time in the movie. And so this 5th dimension is going out of our universe. To visualize this, to be able to visualize this, I want to look only at the 2 dimensions of this equatorial slice through the black hole. And then I see what does that look like as seen in the higher dimensional bulk, we physicists call it. And this is the precise shape of space in that case. The space is highly warped, and it becomes basically cylindrical as we go down here, so that Miller's planet is in orbit at this location, and the black hole horizon is down there. The black hole horizon looks like it's a circle, but it's really a sphere or a flattened sphere because of the rotation of the black hole. But it's a sphere because I have removed one dimension. We're only looking at the two dimensions that are on this slice. So it's a circle. It just corresponds to this circle over here. And so this is the distance away from Gargantua. And the distance goes up and bends out as seen from the bulk, from the higher dimension. Now, in the movie, there are giant water waves that, by contrast with water waves that you see at the ocean, which, when they get steep like this, they bend over and break. And that's, of course, what a surfer rides on, is the breaking wave. But in the movie, these water waves don't break. And so here, let me remind you of what happens in the movie.
Hard these days, a minute to we don't have how's up? Friends, folk up your eyes, hey, spun down and also could mean to us. We're spot. Deep.
Why doesn't the wave break? You see it come in, you see it pass, and it never bends over and breaks. And that's because it's actually a solitary wave, or soliton. This is something that actually occurs in water waves. You see you can see it sometimes on a canal or in a river channel. You don't normally see it in the ocean because it needs to be nearly planar wave. It needs to extend a long distance to the side in order that it behave this way. It can't be something that's localized in all three dimensions. It needs to be translation symmetric off to the side. And here is the actual shape of this solitary wave. The peak is 5 times higher than the depth of the water. I'll return to that issue in a moment. And the issue, what's going on here, is something that is well known to people, to many engineers and to many physicists, but it's really quite interesting. In this or any other way, there is this phenomenon called dispersion, which arises because the water feels the ground beneath the wave. And the long wavelength waves, the longer wavelength stuff, like this stuff out here, it feels it more strongly because the depth is now smaller than the wavelength we're talking about. And they travel faster than the short wavelength waves. You see that at the ocean when the little tiny waves are moving a lot slower than the great big waves. And so that's dispersion. But there's a second effect, that nonlinearity. The higher part of the wave travels faster than the lower part of the wave. And that's the thing that causes the wave to steepen and break. But if you do it just right, the two effects can balance each other out stably. And that's what happens in this solitary wave. And it's a very stable phenomenon. This is described by something called the Korteweg-de Vries equation in physics. For any physicist or physics or engineer student, go read about this. It's really quite interesting. So this is an example of a phenomenon in this movie that plays a central role. There is an issue, however, that wave looks like it's maybe 100 meters high. And so the depth of the water must be about 20 meters, but Cooper's out there walking around in the water. So the water's not deep enough. Now, what's going on there? Well, obviously, they've landed on a submerged island, and the water almost everywhere else is quite deep. It's 20 meters deep. But where Cooper is it's just a submerged island, and the wave hardly feels the island or feels Cooper as the waves sweeps on by. Let me say a few words about tidal gravity. Tidal gravity is this idea that many people have heard about, that if you have an astronaut who falls into a black hole, the astronaut gets squeezed from the sides and stretched from head to foot. It's called spaghettified sometimes by physicists. But it's also the kind of gravity that the moon exerts on the Earth to produce the Earth's tides. And we understand it in the usual way by the moon being here and a gravitational pull that's stronger on the close side of the Earth and weaker on the far side of the Earth. So these arrows show the strength and direction of the gravitational pull. And the gravitational pull is slightly inward on the sides. If you now look at it from the point of view of the Earth and the moon, which are freely falling, so they don't feel, so right at the center of the Earth, the gravity is not felt. The moon's gravity is not felt. So I subtract off the gravitational pull at the center of the Earth. This is what basically the Earth feels. It feels a stretching then. It's the difference between these various arrows. If stretching toward the moon and squeezing from the side. And so similarly, I'm going to skip over some formulas because I don't want to slow down for them. Similarly, for Miller's planet is tidally deformed by the black hole Gargantua as it orbits around it. It's stretched and squeezed, so it has a shape somewhat like this. It's significantly deformed. And that deformation, if you go through some formulas that I'm not going to talk about, turns out to mean that the mass of Gargantua, these rather simple formulas that you can even do just with Newton's theory of gravity, the mass of Gargantua is 100 million times as high as the mass of the sun. That's basically precisely the mass of the great big black hole that's in the galaxy Andromeda, the nearest large galaxy to our own galaxy. It has a 100 million solar mass black hole. And you also, from these formulas, find that the circumference of the orbit of the planet, which is essentially the same as the circumference of the black hole itself, that circumference is the same as the Earth's orbit around the sun. So Gargantua is big, and so corresponding to this orbit, which is just outside the horizon of Gargantua, this orbit is big, about the same as the Earth's orbit. But the nice thing about this movie, and it's all explained in my book about the science of interstellar, is there are a huge number of things that you can understand with some very simple mathematics. If you just learn a little bit of simple mathematics, and I do explain that simple math in the book. In addition, the Gargantua's tidal field that stretches and squeezes, it's a tidal field that is so strong on the planet that the planet is deformed, but Cooper doesn't feel it at all because the tidal force is proportional to how big you are. The planet is enormous, so it feels an enormous tidal force. Cooper is little compared to the planet, so he's not stretched at all. He doesn't feel it. In fact, the tidal force that he feels is the same as I feel right here in Lviv, which is basically nothing. So how are these water waves generated? Well, the basic idea is that here I've moved Gargantua down. I had it before up. And the planet is deformed like this, and you think of Gargantua's gravity pulling strongly on the planet. The planet is in orbit around Gargantua. But as it orbits around Gargantua, it's obvious it's sort of like a pendulum because it's deformed like that, and it just swings back and forth. What's the swinging period? 1 hour. What's the time between waves that you see in the movie? 1 hour. So the waves are generated by sloshing of the water due to swinging of the planet. Why is the planet swinging? Well, it's because as seen by the planet, it's only been in orbit around Gargantua a very short time because of the slowing of time. As seen by us on Earth, it's been around here in orbit for a long time. There's a 60,000 factor difference in time compared to what we would see and what would be seen on the planet. So it's just recently been captured into orbit around Gargantua. It's in a phase of swinging back and forth, and that will gradually go away. Now, this is the iconic black hole image that you see in the movie. And the question is, why does the black hole look like that? And the answer is that the black hole is surrounded by a disk of hot gas called an accretion disk that is about the same as the temperature of the sun. So think of it as being like the sun. It's bright, but it's not so hot that it produces lots of X-rays. It's producing ordinary light. And there's an IMAX camera over here. And a light ray emitted from the top back face of this disk. This disk, you can think of it as being like Saturn's rings. Okay, you know what Saturn's rings look like. The light ray coming off the back top face of the disk travels up and over, being pulled by the gravity of the black hole and down to the camera. So that light ray, that produces the top part of the image. The back top face of the disk looks like this top half ring. And similarly, the light ray from the bottom back face of the disk goes underneath and comes up to the camera. So that produces this bottom part of the image. And then a light ray from the front of the disk goes to the camera and produces this crossbar. So it's all very simple. However, in 2019, 5 years after the movie came out, a collaboration of radio astronomers operated a new kind of telescope called the Event Horizon Telescope, which is made by combining the data from telescopes all over the world, combining them, the data coherently, we say, and working with 1.3 millimeter wavelength radio waves, so it's really millimeter waves. And so it's as though the entire Earth were the telescope. It's as though you had a telescope the size of the Earth. And with that, it was possible to image the black hole at the center of the galaxy M87, the nearest gigantic galaxy to our own. And this is what the image that they built. And this image you compare with Gargantua, and many people have said, gee, they look the same. They don't look the same at me at all. So why do they look different? Why does one have a crossbar and the other doesn't? Why does this one bright on one side and dim on the other? Well, first of all, the crossbar. So Oliver James, who was the chief scientist at the company that did the visual effects for Interstellar, called Double Negative or DNEG, he said, let me take the camera and move it up to the North Pole, out of the equatorial plane and up to the North Pole of the black hole. If I do that, obviously, this is what you get. And then we fuzz this out because the radio astronomers have poor resolution. But then we have to add some brightening on one side and dimming on the other. So here I've explained the shape. But what about this brightening and dimming? Well, that's because this gas around the black hole is moving toward us on one side, on the right side, and away from us on the left side. So there's a Doppler shift. It's shifted to being much brighter on the right side than on the left side. And in fact, I had an argument with Christopher Nolan over this. I said to Chris, we have to put in the Doppler shift. He said, no, you don't. You're going to leave it out. I said, why? We want to get the science right. He said, because I'm getting the science right and you're not. I said, what are you talking about? He explained to me, when you have something that's very, very bright, the human eye cannot distinguish something that is very, very bright from something that's very bright. You cannot distinguish brightness when it's really bright. And that's what's going on here. And similarly, cannot distinguish colors, so you don't see the reddening and the bluing. And he insists that this be the way it is the human eye, although the human eye is supposedly looking through this IMAX camera. But that was the rule of the game, so I gave in. He certainly had a valid point there. So A few words about Interstellar's wormhole. I'm just looking at my watch to see how we're doing. Okay, Interstellar's wormhole. This wormhole is a structure that reaches from the vicinity of Saturn, where Cooper starts out in his spacecraft, through the bulk and up to the vicinity of the black hole Gargantua. Light travels through that wormhole to produce the images that we see. But there's a fundamental problem with wormholes, and that problem is that wormholes implode if you don't do something special to hold them open. This was discovered by my PhD advisor, John Wheeler, back when I was his student. And so this wormhole pinches off so rapidly that nothing can travel through it. So what are we to do? Well, that becomes a challenge of, can a very advanced civilization hold a wormhole open? And the answer is yes, if they fill it with something that I like to call exotic matter. This has to be matter that repels gravitationally instead of attracting. Now, a gravitational attraction is proportional to the mass of the source of gravity. So basically, that means you have to have a negative mass material in there that repels to hold the wormhole open. And so something with negative mass, or equivalently negative energy, because Einstein has taught us that mass and energy are equivalent, you have to have that kind of material, which is exotic material, in order to hold the wormhole open so it won't implode. And I'm going to just skip over some technical details because I want to get to something else. But what I'm going to do is tell you then the bottom line. Oops. I thought I had that right here. Okay, so let me. Okay, so let me tell you the key point here, is that there is something called vacuum fluctuations. And these vacuum fluctuations are the foundation for exotic material, for exotic matter. And when we as physicists make exotic matter in our laboratories, some of us do it every day. We do it in LIGO every day. It's a standard piece of technology, though you haven't been told that. You didn't know we were making matter that anti-gravitates, but we do. But it anti-gravitates so weakly that we don't really see it anti-gravitating, but we know it has negative energy. And the key idea is that if you remove from a box everything that can be removed, then you're left always with random fluctuations of everything that possibly could have existed inside the box. And so you have, for example, particles of light, photons of light, fluctuating in and out of existence all the time. And it turns out that we have strong reason to believe, based both on experiment and on theory, that these vacuum fluctuations have no energy. They produce no gravity. And an example of a vacuum fluctuation is in a laser pointer. I was going to use a laser pointer, but it doesn't work on this screen. In a laser pointer, the photons arrive at the screen randomly, described by what's called a Poisson distribution mathematically. Why? Well, the laser is really trying to produce absolutely steady beam, but vacuum fluctuations, which can never be removed, are present, and they run inside the beam, and they beat against the steady laser light to produce the random arrival of the photons. So vacuum fluctuations, you just see if you have a laser beam and you make you turn it down so it gets very dim, and then you just count the photons as they arrive. You see the effects of the vacuum fluctuation. So it's something everyday life. Now, if you have one region that borrows, one region of a box that borrows energy or borrows vacuum fluctuations from a neighboring region, and this is possible. The vacuum fluctuations can be moved around, but you can't get rid of them, but they can be moved around. Then the region that has loaned the vacuum fluctuations has negative energy, and it's exotic and it will repel gravitationally. The region that is borrowed has positive energy, and it will attract gravitationally. So it's quite remarkable that that is the case. We in LIGO use something called squeezed light as part of our technology, and that is a light where it is oscillating back and forth between having positive and negative energy as it goes along, or squeezed vacuum. And so, as I say, it's part of our regular technology. So you can imagine then a very advanced technology building a device that actually has vacuum fluctuations down here in the throat of the wormhole that are exotic and that hold the wormhole open. And here I'm sketching details, but I don't want to spend the time on it. You can go read my book to understand them. But it's something called the Casimir vacuum. To hold the wormhole open, then, the energy, let me back up and just say, extensive quantum field theory research on exotic matter have indicated that it is likely not possible to collect enough exotic material and put it inside a big wormhole to hold the wormhole open. But we don't know for sure. There is a book by Alan Everett and Tom Roman, if anybody's interested, published in 2012, that you'll find on the web, that discusses this in great detail. But the bottom line is that I and others spend a lot of time trying to understand whether you can get enough vacuum fluctuations in the wormhole throat to hold it open. The answer is we're not sure, but probably not. But because we're not sure, it was fair game for the movie. So in the movie, then I constructed a model for the wormhole that Christopher Nolan liked, and it gave rise to this image of the black hole. And then, and so you can find details of this, and if you're a physics student, you can actually go in and do the computer simulation yourself to build images like that. That's what it looks like to look into one mouth of the wormhole and see out the other side. You're seeing Gargantua and the nebulae in the distant galaxy on the other side of the wormhole as you look into it, or as the IMAX camera looks into it. And it's an exercise for the student to build images like this by propagating light through the wormhole in this particular article that we wrote. And so I'm going to now show you a movie of what it looks like to travel through this wormhole. And so the wormhole is near the planet Saturn, and the wormhole is here, and Saturn is far behind it. So the wormhole is only about 2 kilometers across, but Saturn is gigantic. But because it's so far away, it looks like it's about the same size. And light from Saturn travels around this side of the wormhole to make that image, and travels around that side of the wormhole to make this image. And we're going to travel into the wormhole. And this is a movie that the double negative people made by techniques that I had helped them develop, of what it really would look like to go through the wormhole that is used in the movie Interstellar. So this is the movie that they sent to Christopher Nolan when he said, okay, now we want to travel through the wormhole, what happens? So here we are, headed down to the wormhole mouth. We're about to enter this wormhole mouth to travel through it. We're entering the wormhole. We're traveling through. We've come out on the other side. Gargantua is nearby. I had a telephone call from Christopher Nolan after he saw this. He said, Kip, we have a problem. Would you come to my house? I said, sure. I drove over about a 20-minute drive to his home. He showed me this movie, and he said, that's not exciting enough. We can't possibly use that in the movie. So what do we do? And I said, this is the one place where I agree, you use your artistic license. You don't do it the way it would really be. And so in the movie, you see this trip through the wormhole. This is the way it really would be up until the moment they plunge into the wormhole. Now, this is where he's faking it to make it more interesting. So that's the one place where we compromised in a serious sort of a way. Otherwise, it's pretty much the same. So otherwise, we stuck with the science quite well. So I'm going to now come to the climax and ending of the movie. And let me just say, with regard to that early on in my collaboration with Christopher Nolan, he said to me, I want to have an ending that is mysterious, like the ending of Stanley Kubrick's great film, 2001: A Space Odyssey. And he said, and I want it to be so mysterious that nobody can figure it out without reading your book. And so that's what we agreed on. And so my book, there are 4 chapters at the end that explain the ending of the movie. I'm going to sketch very quickly some aspects of the ending of the movie. But the ending of the movie is highly speculative. So you see this big S up here. Most everything else was not so speculative. So here we have our universe shown as 2-dimensional. I have removed the up-down dimension. And instead, our universe then is this orange sheet. And out back is going into the bulk outside our universe. And so that's the 5th dimension, the out-back dimension, and the 3 usual space dimensions in time, and then the out-back dimension. Now, the trouble with gravity in 4 space dimensions, if you have an out-back dimension, is that the gravitational pull can spread out into the bulk as well as in our brain. And that turns out to mean that the gravitational pull varies as 1 over the cube of the distance to the source. But the experiment says it goes as 1 over the distance squared. And so there's something wrong there. And so you have to modify the space-time structure in order to deal with that. And it was Lisa Randall and Raman Sundram, 2 colleagues and friends of mine at Harvard, who understood how to do this. They said, you surround our universe in the bulk by a piece of what is called anti-de Sitter space. This is just physicist jargon, but what it means is that if you and your pal, your friend, move upward from our universe into the bulk, if you travel up by 1/10 of a millimeter, if you originally were separated by 1 kilometer, then you're separated by 100 meters. Go up another 1/10 of a millimeter, you're separated by 10 meters. Go up another 1/10 of a millimeter, you're separated by 1 meter. And so there's almost no space up there. There's still space, but space is tremendously warped in this really weird sort of a way that actually physicists have reason to believe is deeply embedded in the laws of quantum gravity, but they don't understand the laws of quantum gravity very well. And so this is part of the mystery of understanding new physics. But because there's so little space up in the bulk, the gravitational field lines or force lines, they bend parallel to the bulk. And so you recover a 1 over distance squared gravitational pull. But the trouble with this is there's not enough space for science fiction action in this kind of a universe. And so I changed this by putting a confining brain so that, in fact, you have 3 brains, our brain, which means our universe, this brain, and it sandwiches in a piece of this highly warped space, and above there, space is flat. It's ordinary kind of space. And similarly, a little sandwich down here in ordinary space. And then I had a conversation with Lisa Randall, and she said there's good news and bad news. The good news is this brain world model was proposed and has been explored by the experts in quantum gravity in 2000 by Ruth Gregory and Valery Rubikov and Sergei Zbyryakov. Bad news is that Ed Witten, probably the most famous of our particle physics colleagues and others, showed that this model for the universe is unstable, that pressure in these confining brains makes them go crashing in, and they will destroy our universe when they crash in. That's a problem. Nevertheless, this is what I adopted for our universe, but this means that somehow there is a gravitational anomaly. Gravity is not behaving the way you expect it should behave. And in the movie, you see the gravitational anomaly in that when Cooper tosses a coin in the air, It always falls at the same place. This is early in the movie when there's been a dust storm and the dust fell onto the floor of his daughter's bedroom in stripes that contain a Morse code information about where he should go to find the NASA headquarters. But every time he tosses a coin in the air, it always lands on a stripe. So gravity is striated when you get down close to that floor. It's not behaving the way it should behave. There are a number of gravitational anomalies, and Professor Brand struggles to understand these anomalies. Gravity is not behaving the way it should behave. There should be a great big S up here in the corner, because this is obviously highly speculative. And Murphy Cooper, now grown up, and she's become a theoretical physicist, she is struggling with this, Professor Brand on this. And they're struggling to save humanity from a dying Earth. You see the Earth dying in the early part of this movie. And Professor Brand's plan is that he's going to manipulate gravity. He knows that gravity is not behaving the way it should. There must be some way to control its misbehavior, to turn off the gravitational pull of the Earth or turn it way down briefly so that colonies inside long cylindrical spacecraft can be lifted off the Earth to lift the few 100,000 or 1 million people that are still alive up into space to travel away from the Earth to find a new home. But there's no way they have enough rocket power to do this unless they can turn off the Earth's gravity. This is very speculative. But in fact, it's linked to something called the Jordan Brans-Dicke theory of gravity that I learned about as a graduate student. There are alternative versions of general relativity, including that one, where there are fields that control the strength of gravity. And if Cooper could figure out how to manipulate a field that controls the strength of gravity, then this would be possible. So this is tied to speculative alternative versions of general relativity, in fact. The details of Cooper's thinking about this are on a blackboard. There are 16 blackboards in the movie, and for physicists, there's a huge backstory of the way that Murph and Professor Brand are thinking about what's going on in the bulk in order to turn gravity down. And this is just one of the blackboards. The remark is made in the movie that half of the answer for how to turning gravity down is there, but the other half is in an equation called the professor's equation, which they have to figure out the details. It's a missing piece that is tied up in an equation that is not understood, sort of like the laws of quantum gravity are not understood. Now, for physicists, this professor's equation is the classical limit of a quantum effective action for the laws of physics in five-dimensional space-time. That sounds like gobbledygook, but to some physicists here it will mean something. And this is that the quantum effective action is this S here. And there are fields in here, and they don't understand how the fields are behaving, so there's the unknown stuff in here. And the movie's ending then, they are trying to solve the professor's equation by going in and observing how gravity behaves near the singularity inside a black hole. So this is me and Christopher Nolan discussing how are we going to do this when we were in the process of designing the ending of the movie. And we went through extensive discussions, a lot of them on the telephone, some of them in face-to-face. And let me just back up. And so, as I said, the key thing is that Cooper's going to go inside a black hole. It turns out there are 3 singularities inside a black hole. I won't explain why now. You can read it in my book. But one of them is a gentle singularity. Romilly, the physicist on this trip, calls it a gentle singularity. I call it an outflying singularity. And if they hit that singularity, they may be able to survive. And so they aim to hit that singularity inside the black hole. The other singularities are much more vicious and would probably kill them. But this singularity, like the others, is controlled by the unknown laws of quantum gravity, which may show them through experimental or through observation, show them the missing information that's in the professor's equation. So Cooper plunges into Gargantua.
How do you mean less?
you notice this is the external universe, and originally it was covering almost all the sky, and the black hole was down here below. But as they go down inside the black hole, the ring, which is the gravitationally lensed accretion disk, swings up and around, and the external universe is left inside a little tiny ring above them. But they can still see the external universe. This is a computer simulation of what you would actually see. They can still see it because light can come in through the horizon of the black hole. It just can't go out. That's the nature of horizons. They're one-way mirrors, basically, or one-way membranes. So Cooper, as he is approaching this singularity, tidal forces, as I said, are stronger on bigger things, and they were strong enough on the big Ranger spacecraft to tear it apart, and you actually get a glimpse of the Ranger spacecraft torn apart. He's in his space suit and is dropping down, and he is captured by the tesseract. The tesseract is a cube in 4 space dimensions. It was Christopher Nolan's idea to use a tesseract, not mine. He knew about tesseracts from browsing the web. He learned about them from a child science fiction book called A Wrinkle in Time, a lovely little science fiction book. And so he's captured by this. This is actually a spacecraft that travels into the bulk, built by civilization that lives in the bulk, that is behind the wormhole, has provided the wormhole, has now provided the tesseract. And he travels then up into the bulk, down inside our universe, this brain down here, or membrane as we call it. The distance from Gargantua to Earth is a few billion light years. But up here in the bulk, it's less than the distance between the Earth and the sun. And so he travels that in a few minutes. He's kicking and screaming as he travels it. And then the tesseract docks beside his daughter's bedroom. And here I have a crude diagram where I've turned the tesseract into an ordinary cube. And here is Cooper in the tesseract. This is the bulk coming out of the screen. And his daughter, his two-dimensional daughter, is in this two-dimensional house in her two-dimensional bedroom, which is the other face of the tesseract. And so here he is again with a more proper drawing of a tesseract. Go look on the web to learn why this is a drawing of a tesseract. This tesseract I first saw in a book that it just enchanted me at age 13. And I think if you've never seen a tesseract, look on the web and you'll see why this is a tesseract. Cooper is here. He can see his daughter. If he looks up, there's a light ray comes from the top of her head through this face of the tesseract and that face of the tesseract and down to his eyes. If he looks to the side, he sees his daughter with light rays that come along this path. If he looks through the other side, he sees his daughter by light rays around that path. So he sees his daughter in all directions around him. There's an image of his daughter doing the same thing, but they're seeing from different views. This is what it looks like in the movie. Christopher Nolan has made the tesseract more complicated in ways that I will not explain here. You have to go read the book to understand what he's done. But here is his daughter, and here behind a bookcase, and here behind a bookcase, and there behind a bookcase, over here, down all directions around him, all 6 directions, up, down, east, west, north, south. There are images of his daughter. He's in here. He was kicking and screaming as the tesseract moved back to Earth, and he's now trying to figure out how to communicate to his daughter the information about the professor's equation that she needs in order to save humanity. And he does so by pressing on things called extrusions. There are these long strips that I won't explain now. Again, it's 4 chapters of explanation in my book. Cooper, pushing on extrusions, sends gravitational signals through the bulk interior of this four-dimensional cube, backward in Murph's time to Murph. So in the interior of the tesseract, there is a time machine. And he never experiences the time machine because he doesn't go into the interior. He only is in the face of the tesseract. The only thing he experiences it is gravitational signals that he sends. And he sends them by pushing on one of these extrusions, and that is creating a gravitational signal that travels. And this, nobody's probably going to understand, but this is a detailed picture of what's going on in that, with time travel in the interior of the tesseract. And if you go and if you know about light cones in relativity, and you go stare at this, it's at the end of my book, then you can understand what the mechanism is that the advanced civilization has used to make this time machine. So Cooper pushes on the extrusion to send gravitational signals through the bolt backward in time to Murph. He tells Murph the quantum effective action, the so-called professor's equation. She uses it to control gravitational anomalies to reduce the Earth's gravity for a few hours and save the remains of humanity. And here we are. And at the end, you see them, Cooper and his daughter, now an old woman, inside this cylindrical colony that is on its way to leave the vicinity of the Earth to go find another habitat somewhere else that is more suitable for human life than the dying Earth. Okay, conclusion. Interstellar has actually become a cult film. I know this because I've had many recent requests for screenings of the movies or talks like this, and that wasn't happening a few years ago. In addition, over Christmas, about a year and a half ago, in a small town called Eureka, California, we happened to go through there, my wife and I, and here was a movie theater. Movie theaters are dead in the United States, well, almost all of them, but they sometimes try to have special events to at least keep the movie theater going. So over Christmas, they had a special event. I can't read it very well here with these glasses. On December 30th and 31st, Diggin' Dirt, which is a local funk band, was going to give a concert. And on the 28th of December, they're showing Interstellar. So we went along with a local funk band as a culture sort of a thing. But as I said, in addition, this has motivated many students to become scientists, and I'm very pleased about that, and I thank you very much.
Thank you very much, Mr. Torn. We know that you came here to Ukraine for multiple reasons, and one of them is that tomorrow is your birthday, right? And we know that, and it's a big present for us to have you today. It's a big honor for us to have you today, and you today gave us a present for our audience, and they could have the prize from you, which is a T-shirt and a bag, by donating for our military forces. And tomorrow it's your birthday, so I would like to ask everybody, just give a great round of applause to Mr. Torn for...
Thank you so very much. Thank you. I'll remember this birthday the rest of my life. Thank you.